I will be constructing this as a Lie-Mumford superstack of dimension. So NR here will always denote the Ramond Punctures that we have. So I like to start any talk with the question, well, why am I doing this? Okay, so what is the motivation? Why do we care about these things? So there's maybe two ways of describing this. We can talk about the mathematical version, which is quite simple. So what am I doing? Well, I'm constructing a moduli space. It's pretty historical. We've always been doing this as mathematicians, and this just generalizes moduli theory to include supergroups. So just a bit of a modern take on a classical subject, but for physicists, how this is important is that supermoduli spaces turn out to be the correct spaces over which to integrate to compute superstring scattering amplitudes. So, a few reasons that we might want to do this. So what I'm going to do now is give a brief introduction to superalgebra. I know many of you already know this, but we can just do it again. So I think the best way to understand, maybe let's straight intro to supergeometry. The best way to understand vector superalgebra is take a vector space V, or let's say C, this is better. Then we can use this vector space to create the following two algebras. So just the ordinary algebra is what? It's just the symmetric algebra of the dual of the space. But to create a superalgebra, what we do is we take the exterior algebra of this dual, and on it we place a natural Z2 grading, which is just given by the following. We designate all the edges odd to be odd, and these to be even. In superalgebra, we have a very natural Z2 grading. It's pretty much what you need to know about them. So with this, we can actually already move to talking about superschemes. So what is a superscheme? So maybe a superscheme is a locally ringed space, so a pair given by a topological space I'll call X, a structure sheaf where X is a sheaf of Z2 graded algebras, i.e. it is what? A superalgebra. And we can always sort of decompose this to make evident the grading. Okay, so let's look at some very easy examples of superschemes. So I will describe to you affine space, affine superspace, and projective superspace. So both of these spaces are split, but that doesn't matter so much. What you can think of as affine space is underlying it is ordinary affine mesh space with the Zariski topology. And now, if we maybe now we take the veg of plus n of just the structure sheaf on affine space, and that'll give us a superalgebra. This is an example of a super affine scheme. Affine superscheme. Similarly, we can do this with projective space. Again, we take our underlying space to PPM, but now we want to take the veg of -1 plus n. These are really all you need to know to understand the construction that I'm going to give. Okay, so now one thing that's important in supergeometry is this factor of points interpretation. So maybe on algebraic varieties and smooth manifolds, we know everything about it by its topological space and maybe some regular functions on an open set. That's not true with superschemes. We really need to use this factor of points to to talk about the odd information that we have. So let me just give you the definition. Points of a superscheme X. So what this is we just modeled this ordinarily. Take column X. This is a countervariant functor, category of superschemes. Sets. What does it do? Well, it takes T to the set of all super scheme morphisms T to X.
Could you say a word quickly about y minus 1?
I was going to right after this. You mean the canonical automorphism?
No, in projective space.
Oh, this?
Yeah, that much.
Oh, okay. So the reason I'm doing this is, well, usually you would take the dual of the vector bundle they are taking, but how you can understand this is I can locally purport this on this, okay? So how about we choose, how do I want to say this? Let's do a very easy example with Q11 so I don't have to write everything out. So locally I want this to be Praj CU theta, where this is going to be the generator of the line bundle of -1. So what you can do is I can cover this by the affines. I can show that these are isomorphic. Do you see how I divide by u here? Technically, I'm going to think about this as u having degree -1.
So all three of them have degree -1.
Yes, exactly. So that's how I want to think about it. And this will, I will do this right now because it's going to become important anyway. So I have these two affine superschemes that cover my super projective space. And the gluing that I put on this, I just identify Z with 1 over W, and I will identify zeta with W, 1 over W eta in this case. And that's why I'm calling it off -1. It's because I want to think about this as a line bundle on the underlying projective line. And this has transition function 1 over W, which looks like O of -1. That's fine. It's probably doesn't matter either way, I just feel like it's easier to remember that way. Okay. I forgot what I was doing. Functor points. The only thing I wanted to else point out about the functor points, I'll leave this because I'll use this, is that we can always recover the underlying topological space of a superscheme by sort of probing. I take the spectrum of the point, so just the point onto X. This is going to recover my underlying topological space, but notice I can only recover through the odd information on the superscheme X by probing it with superschemes. And that's why, when we're foreshadowing here, we sort of want to consider families over superschemes too. That's what gives us the odd information, or the interesting information. Okay, so the next thing to point out would be something called the canonical automorphism. So, suppose I give a superscheme, suppose it has local coordinates. Maybe even let's just use C beta. So let this be C11, these are global. Now every superscheme has the following automorphism. It sends it acts as the identity on the reduction and it sends the odd coordinate to, and multiplies it by -1. Call this the canonical automorphism. Every superscheme has this automorphism, and this is why supermoduli constructions are always very stacky, is because of this. We always have this, and we need to account for that when we consider supermoduli spaces. And of course, this acts as you want to. Maybe I'll even write it just. All right. So now let's actually get to some connected supermanifold. Here are some examples. So momentarily, let's forget about compactness just to give an easy example. Then C11 is your standard example of a supercurve. And maybe, remember this is the space like this. Like that. Okay. Another example of a supercurve is P11. Okay. Right. And we define the genus of a supercurve C is the genus of its reduction, C reduced. And I already described how the spaces glue together, so let's keep this because we will use this a lot. Okay, so now that we know what a supercurve is, we can already define what a super Riemann surface is. So a super Riemann surface, or SUSY curve, is a supercurve with a rank 0, 1 distribution, and let me call this sigma. So it's just the rank 0, 1 subsheaf of the tangent sheaf, such that the supercommutator gives us the following isomorphisms. So we have let's look at an example of this. Okay, again, very easy example. If we want to forget about compactness, C11 is another example. And what is going to be the distribution or the superconformal structure on this? Well, let's see theta, the coordinates. C11. Then D is generated by the vector field C is partial. That is our standard example of a super Riemann surface.
Is there a rationale of taking the rank of the both directions to be 1?
What? Sorry.
You know, when you define a supercurve, the dimension seems to be the dimension of the even part. So in principle, you could take the odd part to be of any rank you want. Why are you taking it to be 1?
Supercurve to be 1. Right. There is a definition of a supercurve as a 1n-dimensional super scheme. That is the correct definition of it. In this case, you want to take it to be 1, 1. Why exactly do you want that?
Certainly something you can study.
When you look at the supersymmetric ones, people look at n equals 1 supersymmetry and also n equals 2 supersymmetry, which would be 1/2. But some of the 1 seems to be the basic ones, the ones that behave like a Riemann surface.
Yeah. But no, you can define a supercurve more generally. It's just not what I'm using now. Talking about a super Riemann surface with Ramond Punctures, or RR SUSY curve, just for short, is a supercurve with a degree NR divisor Z. We want this to be maximally disconnected in the sense that we want this to have NR components. Maybe on the back, yeah. Divisor Z. And a rank 0, 1, and D, sigma but now we have that the supercommutator fails to be an isomorphism along this divisor Z. So I want to note that a RR SUSY curve is not a SUSY curve because it doesn't have a true superconformal structure. And Z, or the components of CR, the components of Z are not actually punctures. So sort of both words are wrong. Okay, so why am I saying that? Well, there's no correspondence, unless you have a superconformal structure, there's no correspondence between divisors and punctures. And when I say punctures, I mean actually choosing variables that you have, like a Z naught, beta naught would be an example of a puncture. But when we're talking about divisors, which is a codimension 1, 0 sub-supermanifold. These are not the same as punctures, i.e. these are not the same as Leboeuf-Schwarz punctures. That's what makes this case a little bit more interesting in that sense. We have to come up with new ways of describing these sub-supermanifolds. Okay? So, again, I can give you an example of a SUSY curve with Ramond punctures. That's our favorite example. Again, we have C11. There exists a choice of coordinates C theta such that now I can say E is generated by the vector field. So if you look at that, what is the puncture I chose? Well, my Ramond puncture here was at C equals 0. We can always locally describe a SUSY curve with Ramond punctures in this way. If we're looking at a family over a point, it's not true over arbitrary superschemes. But over a point, this is true. Yeah. So the next thing that I want to point out is what I've just given you a definition of is actually of all of these objects were over points, right? I'm talking about a single supercurve, a single SUSY curve, or a single SUSY curve with Ramond punctures. What I really want to be talking about is families of these objects, and in particular families over superschemes. That's what is going to give us the interesting information. And now I lost the place in my notes. Okay. So let me just at least give you the definition for it over punctures. So we are actually interested in families over superschemes. So the way that you change this definition, at least let's look at this one. So a RR SUSY curve over a superscheme. T is a smooth, proper morphism I from, let's call it X underline T, okay, of relative dimension 1, 1. And again, without writing it all down, the superconformal structure is now a subsheaf of the relative tangent sheaf X over T, and Z is a degree and R unramified or non-ramified divisor over T. Okay, so all of this is saying is that the fibers of this family, the divisor on it has n punctures in some sense everywhere. Okay, so we don't have some sort of collisions that are happening. This is a nice family. This has n punctures over it everywhere. We can think of it as a rank n bundle over T2, to be more precise. Okay. So what I'm going to be talking about is the genus 0 case. So let us talk about genus genus 0 supercurves.
Z is a divisor in what?
I'm sorry, what?
You said Z is a degree in R
Unramified.
divisor. So it's a
Divisor.
divisor in what?
A divisor over T. Maybe you can think of this as maybe O of negative C, and then you can push this forward to T, and this should be a rank NN bundle over T.
But I mean, don't you want to say something about it being a minimal divisor?
Yeah, sorry, so by unramified I'm sort of implying that, okay, yes, we want this to be completely irreducible. We want exactly 4 punctures. Sorry, NR punctures everywhere. Okay, so maximally irreducible. I think minimal divisor, prime divisor, any of those words. Unramified, right, doesn't quite mean that. I mean minimal divisor and then unramified over T. So let's talk about genus 0 supercurves. So what's nice about this is they are all, we can describe these explicitly always, and this is as follows. So let X be a genus 0 supercurve, then X is split, and therefore the total space of a line bundle over its reduction, where J is my nilpotent sheaf. So I have a genus 0 supercurve. So what is its underlying curve? It's a genus 0 curve. So X reduced is necessarily what? The projective line, right? So any genus 0 curve is the total space of a line bundle over the projective line. So Q1. So this means that I can describe X as follows. I'm just using star just to keep up notation. So this is what every single genus 0 supercurve is going to look like. This is quite unlike the projective line because one, we have a distinct supercurve for every integer, and these are all nicely described by this. So, because I'll be using this Penn, let me give you a coordinate description of this. So this is equal to crush of the complex numbers of UV theta, and here I will label this negative m, and this is the weight on theta. And we denote this by weighted P11, m. Locally, the space looks like this. So again, we can take an open subset U where U does not equal 0. This is isomorphic to spectrum C. Again, let us do Z theta theta. And how do we identify this space? Well, on the intersection, we again send Z to 1 over W, but now we send zeta to Wm over times theta. Let me find the place in my notes so that I write down all of the signs correctly. Yes, it should be W minus M. That's why I'm always writing off negative M there, because this is the line bundle with transition functions 1 over Wm. So this is how we do weighted superprojective space. So these are very nice spaces. They're smooth, unlike ordinary projective space. And we know how to describe them explicitly.
They're smooth because the weights are all in the odd directions.
What?
They're smooth because all the weights are in the odd direction.
Yes, exactly. We have no weight. It's just P. It's just the projective line as its underlying space. So there's nothing strange happening. So these are very nice spaces, and these will be very important. So I want to, another way that we distinguish genus 0 supercurves from genus 0 curves is that genus 0 supercurves will have odd moduli. Okay, so these have deformations. We can actually write them down. So genus 0 supercurves have moduli, which I just mean they are not rigid. This is going to be the backbone of the construction of genus 0 moduli space. So I'm just going to abbreviate it like this for now, just because it gets a lot to write. So when I write WP to the M, I just mean weighted projective space 1, 1F. Take the tangent sheet. What we find is the following. So the dimension of this space is going to be 0, negative M minus 1 if M is less than 1, 0, 0 if 3, and 0, M minus 3 when M is greater than 3. So what's going to be really important is the case when M is equal to 1 minus N over 2. What happens is that the dimension of WP 1 minus N over 2, H1, I'm just going to write of this, is equal to 0 N over 2 minus 2. If you can see that this is exactly the odd dimension of the moduli space of genus 0 curves with n Ramond punctures. Okay, so this is going to be my candidate as the supercurve which parameterizes all odd deformations. When I say this is the candidate, I mean this is a good indication that this is where that dimension is coming from, is that these have deformations.
Is there some sense in which the 0 on the left is really a negative 3?
Here?
On the left side of the line.
Oh, should this be negative 3? No, because I'm not looking at anything with punctures. I'm not modding up by the automorphism group here. I'm just looking at the coarse moduli space. Okay, maybe should I say, did you ask, is this the dimension of the moduli space?
Maybe I lost it. This is the dimension of what?
This is dimensions H1, sorry. It's the first order deformations of the tangent sheet of weighted projective space.
So it is dimension of a moduli space.
Right, but that's
It's
only
just H1, not
Yeah. Well, so if I wanted to say this is the dimension of the moduli space of supercurves, that's not quite right because they have automorphisms. So I don't think the Kodaira-Spencer isomorphism holds there. So this is just the coarse moduli space. But it's not even important that this is the coarse moduli supercurves or anything. I just wanted to show, a weighted projective space has a non-trivial first order deformation. There's actually a 0-n over 2 minus 2 dimensional space of those.
I can't quite read. What was the special case on the bottom?
So the special case here, this
Yeah.
one. So this is when m is equal to 1 minus n over 2. And this is sort of a foreshadowing to something.
Okay.
I just want to point this out now. Because it turns out, go on.
And your formula has odd deformations both for negative and positive ends.
Mm-hmm. Yes.
Yeah, that makes sense.
Again, I want to point out this is not the moduli space of supercurves. This is just the space of first order deformations. Supercurves have automorphisms, so we will have the Kodaira-Spencer isomorphism here. And maybe I just make another, maybe let me write this out better, so just that we have it. So dimension H1 of WP 1 minus n over 2 tangent space equals this. And this is equal to the tangent space of deformations of WP. Not a tangent space. The the vector space of first order infinitesimal deformations of weighted projective space. And that's what I really care about. So it just means that if we parameterize weighted, if we take families of supercurves whose fibers are isomorphic to weighted projective space, they will deform in the odd directions. We don't have trivial families.
Can you describe what those curves look like?
Yes, I will. That's sort of the concluding fact. So as I said, this weighted projective space with a weight of 1 minus n over 2 on the odd coordinate is going to be extremely important. So in particular, its automorphism group is going to be very important. So one of the things that we really want to talk about is automorphisms of WP 1, 1 minus n over 2. Okay. Particularly, I want to show that the it's representable. Okay, this has an automorphism group scheme or supergroup scheme. And what I'm going to do to describe this is kind of wrong, but it's also, I think, slightly more enlightening than the proof that I give in my paper, because it's quite complicated, but I just want to give you an idea of how these automorphisms. So again, this is not quite right, but we can think about weighted projective space as follows. We can take the quotient, or we can take the supervector space with 2 odd terms, and we quotient it out by the following action. So we have f lambda acts like this. Right. So if you think back to projective space, this is the way that we write it out as a quotient. Right. So now I'm going to write something that's wrong. I'm just going to say this is WP 1 minus n over 2. And we're going to say that its automorphisms are equal to the automorphisms of this modulo whatever supergroup this group action represents. Yeah, that's not quite right. We don't want to do that. But think about it if you're looking at this normal projective space, and we look at this as the C2 modulo. What do? You basically take automorphisms of C2, you get GL2, this group action is what? GM. You can kind of recover your automorphisms that way, even though it's not quite right. Just to give an idea. So following this idea, what do automorphisms of C21 look like? Or more accurately, what are the automorphisms of the symmetric algebra of this dual? Well, they look as follows. They're just the automorphisms of the superalgebra, obeying the Z2 gradient. Just like if we look at automorphisms of C2, we take the symmetric algebra, we're looking at automorphisms of that algebra. Right? So these look as follows. So notice that I have a bit of a strange looking group here. On the odd coordinate that obeys both the Z2 grading and the degree condition on theta, the weight on theta. And okay, let's E is invertible. This is what these superalgebra morphisms look like. But what do we need to take into consideration? Well, the automorphisms given by this group action, the group that represents this action. How do we think about that? Well, what is it normally? Let's look at the projective line. How do we know it induces an automorphism on that algebra? Well, we say, okay, an automorphism of the projective line induces an isomorphism of the Picard group. Now we look at what does it do? Well, it sends O1 to O1. Then we have global sections. Anyway, this is how we recover this, right? This is how we recover from an automorphism of the projective line the automorphism of that algebra defining projective space.
And lots on the grading in your first line.
Am I grading?
Are the AIs even or odd?
Oh, these are odd.
These are odd.
Yes.
So this is over some parameter scheme that includes.
Yes, because I'm
Okay.
considering this as a functor, so it's over super schemes, so over schemes having odd
So
coordinates.
those are odd, and the other A, B, and C.
Yeah, these are all even.
Okay. Why are the two B's the same?
Oh, because I forgot my alphabet.
So then that's a D.
A, B, C, D.
Okay.
Okay, so now I'm saying a bunch of stuff, maybe it doesn't make sense, but here's the big point that I'm trying to make here. This is the automorphism group of weighted projective space is the automorphism group of this algebra as a scheme which is representable modulo the following. So part of this algebra. So modulo the global sections of modulo of this supergroup. That looks strange, okay? This is the general, just the normal multiplicative group, and this is the odd additive group. Which is a bit strange, but in superalgebra, here's the example, the dual numbers are not a group, right? But if we take the odd dual numbers, those are actually a group, and this is what it represents.
It says 0, 1 there.
Yes, 0, 1, it's the odd additive group. You can think about it as the odd dual numbers, it's the same thing. And where does this group come from? Well, it comes from, we need to mod out by isomorphisms of line bundles, right? So these are like global invertible sections, but global invertible sections on this super scheme are not given by just constants or invertible constants, but rather this group.
Okay, so how does GA act on the group of automorphisms of the graded algebra?
Yeah.
Can you give
Yeah, okay, so let's,
action?
how should I write this out? Right, so they act by multiplication. Exactly. So if we write out a element of this group, on here it looks something like A plus theta, what is this? I equals 0, I equals 1 to n over 2, z to the n over 2 minus I. This is what an invertible section of weighted projective space looks like. Okay, so it's an invertible constant here plus this tail of odd information, and I should be careful here with an odd coefficient. And they act by multiplication, just like the normal invertible sections act, just by multiplication. It just looks strange, but it's not really that strange. It's really just the same thing as invertible sections, but now that group that represents invertible sections, well, it has this tail of no odd stuff. Is that okay? I'll just repeat it. Instead of just the the invertible global sections in weighted projective space look like this, where A is, I suppose it's over T, is something reduced, and Ci is odd. Is even, and the Ci are odd. This forms a group, and it's really just isomorphisms of line bundles. It's the same thing on weighted projective space.
Why can't you put some Z's into the A? Into the even part?
What?
Why can't you put some powers of Z's into the A, into
Here?
the even part?
Oh, this part? It won't be invertible anymore.
A plus Z?
This, you mean here? Just A plus C? No. Because this part is sort of like an invertible section on the reduced part. So it's just constants. So think of GM when I take this direct, this is just the global invertible sections on the projective line, GM. That's why I don't have anything else to do. It's this. Just multiplying by the invertible section right here. So the theorem. So advisor self-conformal. So Ott, and I gave you a very rough idea. I'm not saying this is the proof. Is a super proof scheme of dimension of 1 and over 2. 1 is just the GF, and this is n over 2. Great. So that was probably one of the harder parts of this. And so now we can actually come, and I'm running out of time, so I'm going to hurry up a little bit. All right, here's sort of the big idea. So let sigma, and we can describe it by the following. Z, B, and R are Suzy curve. So we can take the canonical sequence here. Now I can dualize this because everything is locally free, it's not a problem. So dual. Okay. Let's remember this part is important. And now I can take its reduction. When we talk about dual. Dual. Over J, because X is split, this is a projective module, I can take the reduction and I get a short exact sequence of locally free sheaves on X reduced. So locally free sheaves on X reduced, which remember because we're on Genus 0. This is isomorphic to the projective line.
Sorry, what's J?
J is the sheaf of nilpotents.
Oh.
So J, I think it's squared. So in this case, it's just actually the odd component of the structure sheaf. This is just how we take reductions of locally free sheaves. So what did we find? Let me use a more conventional notation. So we reduce everything. Okay. Here, well, remember that the reduction is just the projective line, so this is isomorphic to O of -2. And let's now compare ranks and see what happens. So this is a rank 0, 1. 1, 0. This is rank 0, 1. And this is rank 0, 1. So what do we find? Well, we find what? We have that J is isomorphic to D star reduced, which is, and we also have that D star reduced tensor product is isomorphic to omega on P1. So you see. Okay. This is the big idea. So note D reduced is a, I think this is called a twisted spin structure on P1 along Z. This is how that correspondence with spin structures come up. But the real important part is that we find that J, isomorphic to D star reduced, is isomorphic to O of n over 2 minus 1. Okay? So we find that the nilpotent sheaf, i.e. the line bundle which gives us the superstructure, we find that X is equal to P1 O of, remember I have to take the dual, so what we find now is that the supercurve underlying n in the R SUSY curve is isomorphic to this weighted projective space. Because I found that its superstructure is this line bundle.
This is over a single point.
Yes, this is over a point. So yeah, everything is over a point right now.
And no punctures.
And what?
No
Which
punctures or root punctures.
There's a, yeah,
There is a Z.
Ramond
There is
Punctures.
a
Yeah,
Z.
Z is kind of indicating the Ramond Punctures. Okay, I am really running out of time, so let me make a big note here. I wanted to go through this, but let me say it out loud. So it's really hard over arbitrary super schemes to think about super divisors. We want to get rid of that idea, right? We want to replace it with something that we can actually classify somehow. So what we are going to do is the following correspondence. So super conformal structures, degenerating along Z, okay, just a divisor with Ramond punctures, are correspond uniquely to its perpendicular, which is given by its dual to negative Z as a subsheaf of the cotangent sheaf. Okay, so instead of looking at superconformal structures and these divisors, we can instead classify subsheaves of the cotangent sheaves that look like the perp of D. Okay. So from this now, what we can show is the following. Let me make a list of this. So what can we do? So remember we have a map from WP11 into P1. Because it's split, right? I can show that the Picard group of P1 is isomorphic to the Picard group of WP 1 minus n over 2, which is isomorphic to Z. And using this, I can find that D times the dual negative Z is isomorphic to O of negative 2, where O of negative 2 here is the pullback of the same line bundle on the projective line. Okay, so what does this give us? Okay, maybe I should denote an isomorphism here. If I fix this isomorphism, what does that tell us? This tells us that, how do you say, our SUSY structures on WP 1 minus n over 2 are in bijection with global sections of omega 1, 2. Okay. Where I'm just using the condition that inclusions are given by global sections with the dual. So this is sort of the big point, how we can parameterize things. Now, if I don't want to fix this, so over H naught of WP of invertible sections on here. Okay. That is my correspondence.
Why isn't there an additional choice that's coming from the choice of splitting? Or is the splitting fitting?
No, I think I'm fixing the splitting here exactly.
But I'm fixing it, or is it actually rigid? Is there any choice in splitting, or is it unique?
For the splitting, is it unique splitting? I'm not sure. I would have to think about that.
But you are working with a chosen split.
Yes, exactly. Yeah, I should be able to choose a unique one that acts as the identity on the. I will go back to that just because I want to finish this argument. I hadn't thought about that. So this is the big idea here. Okay. Now, since I'm running out of time. Oh, am I choosing the isomorphism? If I'm fixing the isomorphism with the reduction and the projective line in this case?
No, that's not what I was asking.
Okay.
I was asking if there is a choice in the projection. Because you could imagine that, you know, the line bundle that you have that gives you the odd directions has non-trivial sections, and you can translate by section.
Right. I think that is what I am doing here. But let me get through the big argument and then think about this some more. Okay. Now, I don't want to rush too much, but I might have to. So let me look at the following thing. So this is what I want to classify now. So I create the following punctures. It's a contravariant puncture from superschemes to groupoids. Just ignore that if that doesn't make sense. I'm just indicating that this will be a stack and not a superscheme. And what I do is I send T to RR SUSY curves over T such that they restrict, they are isomorphic. Okay. So I'm saying that the supercurve underlying these R SUSY curves are isomorphic to this product with weighted projective space. I am requiring that. I'll also fix this isomorphism for right now. Actually, let me not. Right? So here's the big idea. So let T be a superscheme. Then T is an odd thickening of T by the nilpotent J. Okay? So now we can sort of use this to translate our moduli problem into a problem of deformation theory as follows. So again, let this be my RR SUSY curve. Now, if I have a family over T, I have that T reduced as an odd thickening. T is an odd thickening, so, and recall that I'm requiring that there exists an isomorphism with this and WT cross T reduced. I'm going to fix those isomorphisms. This is the thing I make here, so I'm requiring this. So what we find is that X is a deformation of WP cross T reduced. Okay, when I fix those isomorphisms. So this means that to X we can ascribe its Kodaira-Spencer class. So kappa X in H1 of WP cross T reduced of the tangent sheet tensor with what we've thickened by. Okay, so I am giving every underlying supercurve, I'm going to ascribe to it a unique Kodaira-Spencer class. Okay. Now, using this, so remember what was the dimension of the space of first order deformations of WP1 minus N over 2? right? This was the odd dimension of my moduli space. Right? So now I'm going to set S to equal spec C of 2, the odd parameters, taking the odd parameters from this space of first order deformations. I will define Z to be the supercurve over S given by gluing the affine charts spec C of Z zeta, and remember these are my standard affine charts for weighted projective space. Along you have V by sending Z to 1 over W, and I send zeta to, where did I put it? W n over 2 minus 1 plus eta I W n over 2 minus 1 minus J, where J is equal to 1 minus 2. Okay, I took a deformation of weighted projective space, and I'm choosing a particular one. And now I'm going to claim that this is a universal deformation for genus 0 supercurves underlying RR SUSY curves. So that's the big idea here. So here, so let sigma over T be an RR SUSY curve over T, and X over T is underlying supercurve. Then there exists a unique morphism phi from T to S such that X bar is isomorphic to the pole dot of Z for T. So I know that every supercurve underlying this family is isomorphic to a pullback of the supercurve C I constructed.
So it's a fine modulus. So it's a fine modulus.
Yes, for just supercurves underlying it. But remember that I fixed an isomorphism. So it's just for deformations. But it's a fine moduli space.
As opposed to what?
If I didn't fix that isomorphism, I would still have the mod Z2 action.
Oh,
That's why it's not fine.
There is something strange. So, in the way you describe the local structure of the supersymmetric structure, you had, dd theta and then theta times dd z, maybe with a z, depending on the puncture. So you could flip the sign only on one of them. That still is going to be automorphism of the supersymmetric structure, which is trivial on the supercurve.
Right, and that's going to be why this becomes a stack. If I'm understanding that correctly. Are you just talking about the fact that SUSY curves with Ramond Punctures have automorphisms?
Yeah, have automorphisms that are trivially on the underlying supercurve.
Yeah, exactly, and that's going to be the Z2 action, and that's why I'm going to have a stack at the very end of this.
they're not trivial on the supercurve.
They're
They're
trivial
trivial
on
on
the
the curve.
On the
No,
underlying.
on the supercurve.
On the supercurve, they're trivial, but it should, I could multiply the odd coordinate by -1.
That would act non-trivially on the supercurve, but you can also act on the cube only by taking dd theta plus theta ddz and send it to dd theta minus theta ddz.
The theta is fixed for you. You don't have to choose it. Training theta. Theta is a coordinate on the curve.
Well, the Z2 action does lift to an action on the conformal structure, on the of -2.
No, it just acts on the distribution. It doesn't act on the.
That is the distribution.
It just changes the distribution.
Yeah.
Let's let her finish.
Yeah.
Okay.
We'll
All
find
right.
it out later.
Well, yeah. Anyway, so we have this. Now what I can show is that if I take a functor x from super schemes variant to sets, that sends T to RR structures. So on Z plus S over T, what I find, so here, so X is representable. Again, I'm fixing the isomorphism phi and represented by the super scheme C and R plus 1 and R over 2 plus 2 plus S. Again, so what did I do? I fixed the isomorphism here with weighted projective space, and I'm fixing this. So all I've done so far is classify Ramond structures on deformations, okay, with this fixed isomorphism. So, but what do I really want? Well, I want to, I don't want this isomorphism to be fixed here, right? It's for any supercurve, for any family, not with the fixed isomorphism. So what I'm going to have to do is what? I need to mod out by the automorphism group of WP at this point. Okay. So I say that M0 and R is isomorphic to the quotient stack, where I'm not sort of confusing the super scheme with the functor X, modulo automorphism of WP. Okay, so this is just a group scheme whose fibers are the automorphism group here. Okay, now I'm going to claim that this is a Deligne-Mumford stock. I'm going to do this as follows. Super stack of dimension NR minus 3. So let me say this very quickly. So this group, the automorphism group, has a stabilizer, namely Z2. Okay. So we have this group Z2, which lives as a subgroup of the automorphism group of WP, acts non-trivially as a stabilizer. Namely, all of X reduced. Okay. But this is the only stabilizer that this group action has on X, so we get a Deligne-Mumford stock out. I know I went over time a little bit, I'm sorry.
That's okay, I slowed you down a lot.
Yeah. So I know this is really fast at the end, and maybe that's good if you ask me specific questions. It might be easier for me to answer them when I don't feel like I'm taking people's time.
Thank you very much.
So what's the generic stabilizer now?
The stabilizer is, so it's all of this reduction. So if I write out, okay, I can give you a long answer. I'll just give the long answer so it makes sense. So what these correspond to are global sections. So remember that the SUSY structures on Z were given by global sections of this space. So these look something like DZ plus, I need to write it down. Let's see. K plus theta, some stuff here, don't remember. Theta, some stuff, and theta. Okay, so if I were to write this out, I think this is I equals 0 to n over 2. AI z to the I. Here we have AI z to the I. This is n over 2, and I think this is that's missing. Okay. The short answer of this is that the coordinates on my super scheme are coming from the coefficients of the global sections of the
So
system.
this guy is a super vector space, right?
Yes, this is
What's
super.
the dimension?
The dimension of this is going to be nr plus 2. where NR plus 2.
And you're reducing.
Yes. Now, remember that I chose an isomorphism. I'm going to unfix it. Now I need to mod out by this group again, because this is the isomorphism group of isomorphisms. Well, this has dimension 1 NR over 2. So now what do I have? I have NR plus 1, NR over 2 plus 2. Now comes the next thing. Now I mod out by automorphisms of WP, right? What is the dimension of this? This is 4 NR over 2 plus 2. Right? So what do I left with? Well, I have NR minus 3, 0 here. The dimension of my global sections. But this has a Z2 stabilizer, which acts, well, it just sends thetas here, these coefficients on the theta to negative theta. But if I don't have any non-zero coefficients, it acts trivially on that. So that's where that's coming from.
Okay.
So what was the stabilizer? What was the answer to this question?
Oh, Z2.
The generic stabilizer is Z1.
Z2.
Just they want to.
Z2, yes. So maybe the recap is this. We want to just figure out what the underlying supercurve is, take the deformations of WP, which is the underlying supercurve, right? Construct a universal deformation, find that every supercurve underlying a family is a pullback of that universal deformation, and then try to classify the Ramond structures on that universal deformation. And we know that those are given by global sections of this twisted cotangent sheaf. Modulo fix the isomorphisms that we fixed. That's the idea. So it's pretty simple, it's just a lot to write out. But if you get the idea, just take this universal deformation, figure out everything about it, pull it back, there, that's it. And then the stabilizer.
So is there any chance of using this to construct the fine modular space in higher genus? I mean, not to describe it explicitly, cross out the word explicitly.
Well, maybe the
just to show it exists.
To show it exists, I think the method could be, the same method could be used if we know what the bosonic moduli space is, which we do. Yeah, and then I mean, if there was some way of figuring out, okay, so what are the underlying supercurves? Do they have a universal deformation? Figure out what's going on in the universal deformation, and thus figure out what's going on in all families. Right? Because all I did here is figure out what's going on over an ordinary scheme, that's not so bad. And then I can figure out what's going on over arbitrary super schemes by just treating families over arbitrary super schemes as deformations.
And one difference is that instead of a single weighted projective space, you'll have a continuous moduli for the weighted projective space.
Mm-hmm.
Because your line bundle is basically a square root of canonical twisted by the NR points.
Mm-hmm.
And that, so in positive genus, that will have moduli.
That makes it a little bit harder to deal with.
I mean, you have the power variety.
Yeah, that's right, we were talking
But
about
that's
that.
not so bad.
Yeah, you would have to take that into consideration too. But I think the process would be the same. Yeah.
Do we know what the underlying supercurves are?
Do I know what?
Sorry, what the underlying super schemes are?
We were just talking about this. So that, if you're talking about the underlying bosonic space, I'm a little bit confused about that. There's two ways to think about it. So let's have a family over an ordinary scheme. It doesn't even matter. Or we can take the divisor and the superconformal structure, right? Now, if I reduce this is a family of genus 0 curves with n punctures, right? So the family is trivial. So we know that the reduction here is isomorphic to P1 plus T.
That's when you forget the location of the puncture.
Yes, yes. I'm not talking about punctures right now. I'm just talking about what is the underlying curve. What is its reduction? Well, maybe we have this. Here's my divisor. Z red is just the degree n divisor of this family.
Right.
Right. So this is what the reduction would look like. Okay, that's the reduction of the curve. But you're talking about what is the bosonic moduli space. So we want to talk about what are supercurves over ordinary schemes. Here's the problem. If we're over an arbitrary scheme, remember that my superstructure, the J, was given by a spin structure on the projective line. Unfortunately, we had a unique spin structure if we were looking at the projective line, but now we're looking at a product of the projective line, so we no longer have a unique spin structure. Instead, because it's alpha, the spin structures on here will look like follows. There'll be fullbacks of the unique spin structure on the projective line tensored with a 2-torsion line bundle on T. Right. So this problem actually turns into a problem of representing these 2-torsion line bundles, which will give you a stack instead of a scheme. Right, so, okay, avoiding some details here, if we're just talking about 2-torsion line bundles, the stack that you get is just point is mod Z2. So I think this is something like, I don't know, maybe the configuration space of n points modulo Z2, some sort of stack that we have.
Right. So this is very interesting, but I think this isn't what I meant to ask actually.
Sorry, you should have just stopped me.
No, this is good to
get.
get. But what I actually wanted to ask is, a supercurve has an underlying supermanifold of dimension 1, 1.
Yes.
And you said that in the case of genus 0, with Ramond punctures, that the super scheme is a weighted projective space. I was asking if we know, for example, in genus 1 with Ramond punctures, what these should be.
I don't personally know that.
Okay.
Well, you look at curve. It's a little bit harder in the super case to talk about.
Isn't it just going to be the bottom, the underlying Riemann surface is the line bundle, which is O of minus the square root of canonical plus the Ramond divisor?
So,
That was the answer. Yeah.
That specializes correctly
Right.
to P1. But it does depend on the location of the point.
Right.
So the phi root of the symmetric product.
Okay. That's a good candidate.
Well, at least in one direction, it should really be checked. And this thing should give you, fixing this data should give you.
Right.
If we run out of questions for now, so, well, let's thank Nadia again. And,